Thank you. So my name is Jordan Bramble. I'm a machine learning engineer at Atrium, and the topic of this talk is detecting signed and unsigned documents with deep learning. I think that the target audience for this talk are people who have some familiarity with machine learning. Maybe you understand how a convolutional neural network works, and you're familiar with evaluation metrics like precision and recall. So now's the time to Google those if you need a quick refresher. I think this talk is really cool because it's an example of applying computer vision techniques to legal documents, which is probably not that common. And I think this talk should appeal to anybody who's interested in applying deep learning to a novel data set. So first, what is Atrium? So we've been around for a little over a year now, and we're a tech-enabled law firm. We mostly service startups and emerging companies in the Bay Area. And we have a unique corporate structure. So we created a tech company that creates the products and technology that the law firm consumes and services our clients. We've done away with billable hours, and we've replaced it with a client-friendly subscription model. And product and engineering focus on building differentiating products that deliver client value and also unlock efficiencies for lawyers. We think a lot about attracting and hiring the best talent and building out teams of expert lawyers. And our strategy has been to sell to startups and scale up with them in their needs. So a little bit more on the problems that we're trying to solve. There's several existing problems with legal services. One is that pricing is non-predictable. It's often opaque. And timelines are also slow, also unpredictable. And there's just a general lack of transparency when interacting with a corporate law firm. On the machine learning and product side specifically, we're focused on automating and mitigating issues with legal documents. So today, searching for a specific document and then extracting the information you need from those documents is a time-consuming and exhausting process. Furthermore, when you want to work with aggregate information across a large corpus of documents, that generally involves keeping track of some spreadsheet, sharing it with people, manually combing over documents and plugging things into a spreadsheet. We're trying to replace that. We're trying to use machine learning to turn these documents into data. So what we're focused on doing is building out a structured metadata profile of any document that we receive. So a bit more on what that looks like in practice. So when we receive client documents, we apply optical character recognition, and then we apply several machine learning operators to the document. And then we bring a human in the loop to audit and review both the documents themselves as well as the outputs of the machine learning models. Then we use this structured representation for search and retrieval of the documents in order for both our clients and our lawyers to perform legal tasks. So that could be anything from a venture capital financing, an incorporation, or a contract negotiation. And we use the structured data also to generate new documents, like a cap table, for instance. So we accomplish this with three machine learning technologies today. The first is document classification. So we classify a document, and we use that classification to route a document to the appropriate structured predictor, which my colleague Zach Witten just spoke about in the last talk, for those of you that were here. So structured predictions, that's how we annotate fields like counterparties and effective dates in documents. And then if the document type is one that we expect to require a signature, we run a signature detection operator on the document. And that's what the remainder of this talk is going to focus on. So why do we care about signature detection? Well, right now, manually detecting whether or not a document is signed requires the time and effort of skilled individuals, namely paralegals, who could dedicate their time to more important things. Also, having unsigned documents poses significant legal risk for our clients. And then another thing that happens is when clients upload a batch of documents, some percentage of those are going to be drafts of each other. So you can determine which documents are related to each other, but then you need to be able to determine which document is the final copy in that batch. So the presence of a signature is actually a strong indicator of which one is final. And let's go a little bit into the history of signature detection and some of the literature that's out there. So banks do this with checks today, but they're fortunate enough to work on a much more constrained problem. They're usually only ever looking for one signature. The documents are templated. You know where a signature would appear. And then outside of banks and law firms, signatures are really not all that important from a business standpoint. So there hasn't actually been a lot of improvement in recent years in the ability to do this. But there is a publicly available data set called the Tobacco 800, which misleadingly actually contains almost 1,300 labeled images, but they've only labeled signatures. So none of them have like unsigned labels. So several papers have been published using this data set. Some of them are using the signature as a mechanism for retrieving similar documents. Others are focused on classification. But what you commonly see is researchers will apply these somewhat arcane, either like rule-based approaches that are specific to detecting cursive script, or they'll use some other manual feature extraction technique, and then they'll run a classifier afterwards, and that may be a neural network, it may be a support vector machine. As far as I can tell, the state of the art on detecting signatures is 92.8%, and I haven't been able to find a lot on detecting unsigned signature boxes in documents. So if anybody has any experience with that, I'd love to talk to you. And for legal documents specifically, you might be detecting an arbitrary amount of signatures in unsigned signature boxes, and the locations where they might be in a document can be somewhat arbitrary as well. So in addition to using the Tobacco 800 data set, we started out with 12,000 labeled documents of our own, and over the last few months, we've scaled up to more than 40,000 labeled document pages, and that results in 10,000 unsigned signature boxes and 4,000 signed signature boxes. So one approach to solving this problem and an appropriate method would be using convolutional neural networks. And the simplest way to do that would be to just do binary classification. So you would return a probability distribution for whether or not the document is signed. And that's actually the first approach we took, just to see what kind of results we could get. So if you're not familiar with convolutional neural networks, I'll give a quick high-level description. The basic idea is the network is applying these fixed size filters that stride across the image, and they're applied to the RGB channels of the image. And then they're computing a nonlinear activation the way a standard neural network would. Then there's also an operation called max pooling that allows you to downsample the data by selecting the max value in some fixed region. Then generally at the end of the network, you'll have a fully connected layer. After this, you've extracted all of the features you need in order to make a classification. So to that extent, you can think of the hierarchical layers in the network as the earlier layers are learning sort of simple shapes, edges, things like that. And then the hope is that the later layers will be learning more complex things like how to detect handwriting and hopefully how to detect signature boxes. So now that we're starting to get into deep learning, I want to address a few kind of common misconceptions about deep learning. The first is that doing deep learning requires large amounts of data. This has become, this was true at one time. This has become less true because transfer learning has taken off. There's a lot of large publicly available data sets that you can use to augment your own data. And there's also a lot of pre-trained neural networks that are published that you can transfer learn on top of. If you're not familiar with transfer learning, I'll define that in the next slide. The other is that it requires deep expertise. So this is kind of true. I don't believe that it requires any more expertise than other approaches. It's just that you're shifting where you need that expertise. So instead of having to learn like manual pre-processing techniques that are very specific to the problem you're trying to solve, you just operate on raw inputs. So now you're having to build more expertise in some open source library that's pretty hard to use compared to scikit-learn. And then the final misconception that I often hear is that only big companies have the data and the compute in order to do this. I think this is another one that's really changed in the last year. There's a rich ecosystem of startups now that are helping companies scale up data labeling operations, as well as giving affordable access to GPUs to train on. So I mentioned this concept of transfer learning. So I want to sort of get into the intuition behind that. So we mentioned that The earlier layers in a network are learning very simple things like shapes and colors and edges. Well, it turns out those are pretty common to all computer vision problems. And so the intuition is, and it's been shown that you can actually get better performance out of a neural network if you train on a massive general data set, so something that has lots of classes of images, lots of representation for each class, and then you freeze the earlier layers in the network, and you change the output the output layer to better represent the problem that you're trying to solve, and you just update the weights on the last few layers. So this greatly reduces the time it takes to train a model, reduces the amount of data that you need, and all in all, it's just a less volatile experience. So what you've started to see is it's less common to train a custom neural network from scratch, just because of the difficulty associated with that versus doing transfer learning. But we did, mostly for the sake of like benchmarking, just to see what kind of performance we could get, we did attempt to use a custom neural network to do binary classification. So I defined this network. It's got a softmax output that returns a probability distribution of whether or not the page is signed or not. It's pretty standard. We use 3x3 convolutions, 2x2 max pooling, and we use ReLU activations. And it actually gets really good results. We're able to get above 90% accuracy of classifying whether or not a page is signed. But there's only one problem with this approach, which is consider the case where you have one signature present on a page, and you're able to detect it, but you're also missing another signature. So a binary classifier would actually return, this document is signed because it's detected a signature. So these gray boxes that you see on the image, that's just me like anonymizing people's names and stuff like that in the document. So what we actually want to be able to do is be able to localize two classes, signature boxes, which contain a signature, and unsigned signature boxes. So what we actually want the neural network to give us is a class label for what we're detecting, and we want an x and y coordinate of the midpoint and a height and width for the bounding box surrounding that object. So you might be asking, how does this change the architecture of the neural network I'm working with? Well, it turns out not a lot changes. So we're changing the output to give us a confidence of whether or not an object is detected, the x and y coordinate, and the height and width of the bounding box, and then a distribution of the class label. Now I've simplified this a little bit because what you're actually doing is you're going to partition the image into a grid, and the network is actually going to output a volume. So you'll have one of these y outputs for each cell in the grid that you've partitioned. So in this example, there's a 3x3 grid, and it's a 3-class problem, so the output is a vector of length 8. So the network would actually output a 3x3x8 volume. And there's a little bit more math going on. So there's the x and y's, they go through some sigmoidal function in order to constrain them to be between 0 and 1 because they're encoded relative to where they are within the cell that they're located in. And the height and width go through like an exponential parameterization to make sure that they're greater than 0. They can also be greater than 1 because they're expressed as a fraction of the width and height of the bounding box that their midpoint is in. So the technique that I'm hinting at, it comes from a paper by Joseph Redman on YOLO, which stands for You Only Look Once. And the reason this approach has become so popular is because it allows you to predict precise bounding boxes for objects with only passing over an image once. So some other techniques that exist require you to slide a neural network over a fixed size window and so you're making calculations at each step. Whereas with YOLO, you only have to do that once. And then there's some other techniques that involve applying segmentation algorithms to try to infer where an object might be. I also think YOLO is pretty simple to understand. And I think there's just a few kind of key concepts that you need to grasp in order to understand how it works. The first, which we hinted at in the last slide, are grid cells. So what you'll commonly see is you partition an image into like a 19 by 19 grid. And then the neural network outputs this volume, and that allows you to detect one object per grid cell. But what if I want to be able to detect more than one object per grid cell? So the paper introduces this concept called anchor boxes, and the intuition behind anchor boxes is, let's say I want to be able to detect 5 images in each cell in the grid. Well, what you do is you just make the output 5 times longer. And you would go through your training examples, and you would pick some shape of an anchor box that kind of most reflects the objects that you're trying to detect. And then at training time, you would assign each example to the segment in the output that has the most overlap with the anchor box associated with that segment in the output. And what I mean by overlap is they use a metric called intersection over union in order to do this. So intersection over union is just meant to measure the overlap between 2 bounding boxes. So you just take the area of the intersection of those boxes and divide it by the area of the union of those boxes. Now, the other thing that YOLO will do is it'll output multiple detections for the same object, and you want to be able to clean those up. So it introduces an algorithm called non-mech suppression. So what that means is discard all of the bounding box predictions that have a confidence of less than 0.6 or some hyperparameter of your choosing. And then iterate over the bounding boxes and focus on the one with the largest confidence. And then discard any other bounding box that has an IOU with that of greater than 0.5. And this cleans up the predictions quite nicely. Along with this paper, they published, and they've open sourced a pre-trained network. So we actually perform transfer learning on top of this network that the paper published. So I'll go into a little bit of our methodologies for how we've solved this problem. So one of the YOLO papers actually proposes this idea of using unsupervised learning to learn what your anchor boxes should be instead of handpicking them. So the idea is take all of your training examples, set them to have the same midpoint, and then for the k number of centroids of your choosing, cluster in the width and height space and use IOU as the distance metric. So we've done this for 3 anchor boxes, and we're able to get an average IOU of 0.83, whereas so 1 would be perfect. The other concept that we use, so it's not in the paper, but it is in the open source implementation. It's called warm-up batches. I haven't seen a good theoretical justification for it, but the idea behind it is, in the first few epochs of training, constrain the problem a bit by setting the bounding boxes to be the same as the anchor box that it's associated with. So the intuition behind this is it should help the network familiarize itself with the data set a bit before trying to work on a much harder problem. And it's been shown to work in practice. So if anybody has a good theoretical justification for it, I'd also like to hear a bit about that. We use a really small learning rate, which is common with transfer learning. And what we do is every 4 epochs where the loss doesn't improve, we cut the learning rate in half. And then we trigger early stopping after 7 epochs without improvement. And then what we do is after early stopping is triggered, we actually restart training 3 times. So this is incredibly inefficient. But what it does is, so you bump the learning rate back up, and then you run a few more warm-up batches, and so you'll see the loss temporarily go back up, and then it'll start going down again. What we've found this does in practice is it allows the network to explore the loss surface in a more nuanced way. The other thing that we do is we've experimented with between 10 and 20% negative sampling. So we try to include a few images in the batch that don't have any detections at all, just to see how that affects the results. And we've tried augmenting and enhancing our data in specific ways as well. So in addition to training on the raw RGB images, we've also used optical character recognition to apply some enhancements to the images, which I'll tell you about in the next slide. And the other thing that we've experimented with doing is constraining the problem to a single class problem. And we allow 100 max epochs. In practice, though, across all 3 training sessions, we get somewhere between 60 and 75 total epochs trained. So I mentioned optical character recognition. So optical character recognition is just extracting text from images. We rely on Google Cloud's OCR API in order to do this, and that returns these bounding boxes for every word in an image. And then what we do is we've tried to augment the data in such a way that we try to highlight words in a document that appear in close proximity to signature boxes. And Google OCR is also able to recognize handwriting, so we've like highlighted that as well. This is not really the best example because it's like it's highlighted signature down here, but it's not anywhere close to a signature box. But I like this example because you see the model detecting both signed signature boxes and unsigned signature boxes in the same image. So the idea behind this is like the higher contrast should make it easier to detect. I'll tell you a little bit about how we train and deploy these models. So we train on AWS deep learning AMIs, and we use Terraform to orchestrate the provisioning of a GPU instance. And that provisioner will go and check out the GitHub repository, download all of the data from S3, and it'll spin up a TensorBoard server and a Jupyter Notebook server that you can log into. And it'll set up SSH and things like that, but you can also kick off the training of a model without ever SSHing into the server. And then generally, once a model is done training, we'll actually just destroy these as well. So we can just spin them up and destroy them as needed, basically. So we train with Keras with a TensorFlow backend. And then in order to deploy these, we write the weight graph to an S3 bucket, and that gets read into a Flask app that's deployed in AWS Fargate. So Fargate is AWS's container orchestration tool. So we deploy a microservice with that, and that microservice is consumed by our data processing pipeline. So now I'll jump into our results. So some of the kind of takeaways here are, it seems to us like including two classes actually, so like including signature boxes actually improves performance on being able to detect signature boxes. So the classes are so interrelated that the presence of both helps learn the other one. And then the other thing is these like manual kind of pre-processing techniques we've tried, it's like unclear if they're actually making a strong difference. Like the results are pretty much the same across both RGB and OCR. So some of the takeaways from this talk are that, so deep learning might not always outperform approaches that leverage domain-specific knowledge. But being able to leverage deep learning, it can actually reduce your development time. So you're trading off time spent applying pre-processing techniques, learning things manually about your data set, and you're exchanging that for time spent training models. So to that effect, it can enable your team to produce a solution faster because you don't have to handcraft and extract these features from data. You just get to operate on raw data. The other thing is some of the enhancement approaches that we've experimented with, they don't seem to be particularly high leverage. What we found to give the best effects was just labeling more data. So by labeling 3 times the amount of data that we had before, we were able to get a 20% increase in recall just by doing that. Another thing that we found is that deploying the weights of a neural network that operate on raw input can actually be a lot less time-consuming than having to port over pre-processing code into your application. And the final thing that I want to leave you with is, all of this being said, using deep learning is not an excuse for not diving into your data set and building up specific knowledge of it. One of the great things about these localization networks is they output these bounding boxes, and you can go back and look at examples and see what the network is misclassifying, what it's missing, and that should give you some inference on how you should label data going forward, what your data labeling strategy should be. So in other words, if you notice trends of certain objects that you're missing commonly, well, go back and label more of those and then include them in your training set. So thanks for having me. Feel free to reach out and contact me. I'll hang out a bit. We can talk, and I'm happy to take a few questions now as well. Thank you. Any questions? Yes?
So are you trying to detect signatures to make better legal documents so that people don't forget to sign them, or just because you want to know if you have to send them back to see if they're signed?
That's a really good question. So the question is, a bit more about what our motivation is behind detecting signatures. Are we trying to create better documents that are easier for people to remember to sign? Or are we just trying to be able to detect things so that we can send them back? I think it's a little bit of both. So one of the things, so Zach mentioned in his talk, one of the things we want to be able to do is standardize more document types that are used in legal. Generally, that requires you to be like a dominant player in a specific space before you can kind of set the market. But right now, the primary motivation is it allows you to filter out drafts, because drafts are commonly unsigned. And then being able to detect unsigned documents provides legal value to our clients, because we're like mitigating risk for them. But yeah, we definitely don't want to be like spamming you with unsigned documents all at once.
Yes? Do you think YOLO is like the right signature detection model to use, or like what are some other like CNN?
Well, so the question is whether or not YOLO is the best approach to localizing in documents. One of the reasons I really like YOLO is one, because it's fast, but also because there are just a lot of good open source implementations out there. For a lot of the other ones, it's a bit harder to get like grad student code up and running sometimes. So, yes.
Follow-up question to that. I think there is also faster CNN or fast RCNN.
Yes, so that's one of the ones that I believe, correct me if I'm wrong, but I believe that's one of the networks that applies like a segmentation algorithm up front, and it tries to infer where certain objects might be.
Yeah, I'm not 100% sure, but I was just wondering, like, do you know more about that? I have just heard about it.
So we looked at it early on, and I think that one of the reasons that we didn't go with that, and we didn't actually evaluate this empirically, but the theory being, if you're relying on a segmentation algorithm up front, that might not work so well when you're trying to detect the absence of something. So in other words, like and for the unsigned images, we're trying to, or the unsigned signatures, we're trying to draw a bounding box in what is effectively like white space. So that was one of our concerns there, so we didn't evaluate it. Yes?
So you have two models in place. One is to detect a signature box, and then if it's signed or not, or how like it's working.
So that's another one of the things that I really like about YOLO, is you get to do this in a single pass. So it can detect both classes, and so actually what we're doing is we're treating this as a two-class problem. So you have signature boxes, and then you have ones that would contain signatures and ones that don't contain signatures, and those are our two classes. So when I said sometimes I use signed signature box and signature box interchangeably. So the way it's actually set up is we have unsigned signature boxes and signed signature boxes. Those are the two classes that we're localizing. Yes?
So it sounds like you really want recall up to 100%, right? Ideally, so in the real world business case, what are you seeing as the consequences of passing on unsigned documents that your model is missing? Like, how are you dealing with that?
Yeah. So that's exactly right. So we bias towards having really high recall. Because all of this, there's a human in the loop for all of this. So a classification is made, and a human is going to review all of this. So what we've found that the power of machine learning is, in a lot of these cases, is previously the human would be like combing through a document manually to find certain things, like flipping through document pages. And being able to have a nice bounding box for something that you want them to see allows them to go directly to that. And so one of the things we might want to experiment with is like what we should do with different confidence thresholds and like how we should serve that data. But this has been in production for a very short amount of time. So yeah, right now a human reviews every document basically, and we want to eventually be able to either drastically reduce the time that they spend reviewing documents, or being able to reduce the portion of documents that they actually have to manually review. So the first one is a bit easier to reduce the amount of time that they have to spend.
Are you showing them, it sounds like you're showing them a bounding box then for every document?
Yes, and not just for signatures, so it'll be for other fields as well, like the counterparty, the effective date.
So you're highlighting a bunch of stuff for them?
Yeah, and then they can just click through the suggestions. Yep.
What kind of pre-processing have you tried? I think that at least rotating would help.
Yeah, so that is actually handled by our implementation. So we just use Keris's like standard data augmentation. So that'll apply like small rotations, crops, and it'll do like other kind of like sharpening and brightening tasks and things like that. So we allow like the Keras library to handle that for us. The manual pre-processing techniques that we've applied have been trying to do things with OCR outputs. So we've tried to like create these like high contrast images that highlight certain words in documents. We've tried to, so the page number, like the page number of a page in a document is also somewhat reflective of whether or not you would expect a signature. Because it's like, I think, I'm kind of paraphrasing, but I think it's like the fourth page of a document is most likely to have a signature. Yeah, well, the last page, but like across all document sets, like page 4 is the most likely. But and I'm kind of paraphrasing that a little bit. So like another thing we've tried to do is like shade the pages based on where they are in a document.
I'm thinking of leases, but leases have a lot of little initializations on the sides too. Or do legal documents have those as well? Is that something you're trying to flag?
I've seen very few examples of that in legal documents. We're kind of fortunate that most of the legal documents that we work with for the tasks that we perform, it's kind of like a fixed space, and some of them are somewhat templated. Some are templated more than others, but. Cool, well, thanks a lot. Thanks for having me.